First of all, a few basics. What is a rational function? A rational function is a function in the form f of x equals n of x over d of x, where n of x and d of x are polynomials, and d of x is not equal to 0. In other words, a rational function looks like a fraction, but you're going to have variables in the numerator and denominator. Now, actually, you may not have a variable in the numerator, but you must have a variable in the denominator for this to be a rational function. And as with any fraction, the denominator cannot equal 0. The domain will include all numbers except those values of x that would make the denominator 0. Now, that's not saying that x can't be 0. X can be 0 as long as putting 0 in for x does not make the denominator 0. So what you want to do is set the denominator equal to 0 and solve. And whatever you get, those are the x values that you cannot use. Those are the ones that are not in the domain. Now, rational functions will have asymptotes. If we look at the graph here, and here we have two different rational functions. The one on the left is the most basic rational function, 1 over x, and the one on the right has had a few changes made. It's been stretched, it's been translated. Note that the behavior of the graph as it nears the forbidden x values, note what that is. For the first one, 1 over x, x is not allowed to be 0. So look at what happens as the graph gets closer to 0 from both the right and the left. Now remember, x equals 0 is the y-axis. So you're looking at what happens to the y values as the x values get closer and closer and closer to the y-axis or to 0. In the second graph, the number that you cannot allow x to be is 1, because x minus 1 is in the denominator, and 1 would make that 0. And you want to look at what's happening as you approach 1 following the graph from the right and from the left. Look at what's happening to the y values as the x values get closer and closer to 1. And what you notice in both of these is that as the x values approach that number that they are never allowed to reach, that one branch of the graph goes towards negative infinity, while the other branch goes towards positive infinity. One goes down and keeps going down and will go down forever. The other side goes up and will keep going up. Observing vertical and horizontal asymptotes, those are lines that the graph will approach but will not cross. It's really easy to determine where the asymptotes will be without graphing the function. And the vertical asymptotes we've really already talked about. Those are going to be at the values of x where the denominator of x equals 0. Unless, you knew there had to be a complication here, unless you are able to cancel part or all of the denominator with part or all of the numerator. In other words, factor the denominator, factor the numerator. Okay, whatever x values make the denominator 0, those are kicked out of the domain. Those cannot be in the domain. Now, whether or not they will be an asymptote depends on whether or not you can cancel one of the factors in the denominator with the factor in the numerator. If you can cancel one of those factors in the denominator, then that x value, instead of being an asymptote, will be a whole. Now, horizontal asymptotes, we learned to do this last year. Actually, this should be a review. We find those by comparing the degrees of the numerator and the denominator. The degree, remember, is the highest power on any variable in the expression. And we use this phrase, Bobo Botan eats DC. Now, learning the phrase is great. It doesn't do you any good, though, if you don't know what the letters stand for. So as a reminder, Bobo means bigger on bottom, y equals 0. In other words, if the larger power, the larger degree is in the denominator, is on the bottom, then y equals 0 is your horizontal asymptote. Botan stands for bigger on top, none. If the bigger power, the bigger degree is on the top, then there is no horizontal asymptote. And eats DC stands for exponents are the same, divide coefficients. So if the powers on the top and the bottom, the largest power is the same, then you look at the coefficients in front of those x's that have that high power, and you divide it top over the bottom. Now we'll do some examples of these. Okay, here are a couple of examples. And with these examples, what we're going to do is we're going to see if we can find any vertical asymptotes or holes, and that's all we're doing in graphing it. So let's look at the first one. All right, give this a try. Pause the recording, give it a try, and resume to check your answer. Okay, so we can't cancel anything here. You cannot factor the top, so nothing's going to cancel, which means we set x minus 3 equal to 0. We get x equals 3. So we're going to have a vertical asymptote at x equals 3. Remember, vertical is up and down. X equals 3 is the vertical line that crosses through 3 on the x-axis. And you can kind of imagine there being a dotted line there that this graph will never be able to cross. Now try this one. Remember, factor the numerator first if you can. Pause the recording, give it a try, and resume to check your answer. Here's what the graph looks like. If you graph this on your calculator, what we need to do is we need to factor the top, and we'll notice that x plus 2 cancels. Now, we still can't allow x to equal negative 2, but because it cancels, it's not actually going to be an asymptote, it's going to be a hole. And the hole, if you look at the graph, you can kind of tell where the hole is going to be. It's going to be at the point negative 2, 1. If you're wondering how do you find the y value, like here it's kind of obvious, but how do you find that? What you do is you take the value of x, where the hole is, negative 2, and you put it into the equation after you've canceled that common factor. So after we cancel the x plus 2's, we're left with x plus 3. Put negative 2 into x plus 3, and you get 1. So the hole will be at negative 2 for x and 1 for y. All right, now try this example. We're going to find the domain of the function and discuss the behavior near the excluded x values. Okay, we talked about this a minute ago. Pause the recording, give this a try, and resume to check your answer. Okay, so the domain x cannot be 1, and if you look at this, as x approaches 1 from the left, the graph goes down towards negative infinity, and as x approaches 1 from the right, the graph goes up towards positive infinity. You can double check this by graphing it on your calculator. By the way, just a word of caution, since we're getting into these rational functions again, remember that when you do graph these on your calculator, you're going to want to put the numerator in parentheses and the denominator in parentheses. Now with this particular function, since the numerator is just a single value, it's just 1, it would be okay to not have parentheses there. But anytime your numerator or denominator is more than a single term, you have got to put it in parentheses, and especially the denominator. I would always make sure to put parentheses around that denominator. It's better to use the parentheses when you don't need them than to not use them when you do. Similar problems, so pause the recording, give this one a try, and resume to check your answer. Okay, so if you factor the denominator, you get x plus 1 times x minus 1 because this is a difference of 2 squares. Or you could just set x squared minus 1 equal to 0 and solve. In both cases, you're going to get negative 1 and 1. So x cannot be negative 1 or 1. So now we've got 2 asymptotes. So we have to describe what happens on both sides of both asymptotes. So if you're looking at the graph, as x approaches negative 1 from the left, f of x, the graph goes up toward infinity. As x approaches from the right, it goes down toward negative infinity. As x approaches positive 1 from the left, it goes down, and then as x approaches positive 1 from the right, it goes up. So you're just describing, does it go up or down as your x values approach that particular value that it's not allowed to really equal. Okay, this time we're going to find the vertical and horizontal asymptotes of the graphs. Remember, your vertical asymptotes are going to be where the denominator equals 0, and horizontal, you're going to use Bobo Botan eats DC. Pause the recording, give it a try, and resume to check your answer. So we have a vertical asymptote at x equals 0. If you set the denominator equal to 0 and solve, you get 0. And the horizontal is y equals 0 because we have a bigger on bottom situation. The top doesn't even have an x, much less with a power. So the bigger power is on the bottom. The power on top is really 0. It's x to the 0 because it's not there. And we use Bobo, bigger on bottom, y equals 0. Okay, same thing, new problem. Give this a try. Pause the recording while you're doing it and resume to check your answer. Again, our vertical asymptote is going to be 1, -1. It's the same denominator as before, as we did a couple problems ago, not the last one, but 2 problems ago. Horizontal, we have none. This is a bigger on top situation. The degree of the top is 3. The degree of the bottom is 2. So this is bigger on top, which means there is no horizontal asymptote. Pause the recording, give it a go, and resume to check your answer. Okay, so the first thing we're going to do on this one is we are going to actually factor everything because we need to see if anything is going to cancel. And we see that the x plus 1 will cancel. Now, remember, what that means is that x still cannot be -1, but instead of an asymptote, we're going to have a hole. So our vertical asymptote is going to be x equals 1/2. Our horizontal, let's go back to the original problem. Our degree on the top is 2, our degree on the bottom is 2. Exponents are the same, so we divide the coefficients. The coefficient on the x squared in the numerator is 1, and the coefficient in the x squared on the denominator is 2. So 1/2 is 1/2. And by the way, if you're wondering what would be the y value for that whole, simply put -1 into the reduced problem, that last x minus 4 over 2x minus 1, and we would get -5 over -3, so 5/3 would be the y value at that whole. Now a word problem because we all love them ever so much. So let's look at this one. The cost in dollars of supplying recycling bins to P% of the population of a rural township is given by C equals 25,000 P over 100 minus P. 0 is less than or equal to P, which is less than 100. Now, before we move on, let me say this. That last part is telling you the range of values that P can be. Why is that important? Well, normally when we work with a percent, we are going to change it to a decimal. But this little bit of information here tells us that the formula was actually based on leaving it as it is. So in other words, if P is 10%, you're going to actually put 10 into the problem, not 0.1. That's what that 0 is less than or equal to P is less than 100 is there for. It's not part of the actual function. It's not something you need to compute. It's just to tell you, hey, normally you'd make your percentage a decimal. This time, don't do it. Leave it between 0 and 100. All right, so what you're going to do with this is you're going to graph the cost of the function. Again, just graph the C equals 25,000 P over 100 minus P. You're going to find the cost of supplying bins to 15, 50, and 90% of the population. There's several ways you can do that. You can do it by looking at the graph. You can do it by finding those values on the table for X. You can do it by straight putting them into the problem and solving. And then according to this model, would it be possible to supply bins to 100% of the population? Would it be possible? Okay, pause the recording, give this a try, and resume to check your answer. Okay, so we have our graph. And notice the window here. Our X is going from 0 to 100, which makes sense because it said P should go from 0 to 100. They've got their Y value going all the way up to 300,000. And then for B, you see the various amounts there, the various costs involved. Okay, and then they just solved them there. And then for C, as C approaches infinity as X approaches 100. In other words, we have a vertical asymptote there, which should not surprise us because when P is 100, the denominator is undefined. So we have an asymptote there, and it's not possible to supply bins to 100% of the residents because the model is undefined for that value. Okay, here's another example. Psychologists have developed mathematical models to predict memory performance as a function of the number of trials n of a certain task. Consider this learning curve. P equals, and we got 0.5 plus 0.9 times n minus 1 over 1 plus 0.9 times n minus 1. And again, the n is greater than 0 is just telling us that n cannot be a negative number. It's not even going to be 0, which makes sense because here's what n, it says P is the fraction of correct responses after n trials. So you can't have a negative number of trials, and really even 0 trials doesn't make any sense because if you're not going to try it, you're not going to learn to do it. So n has to be greater than 0, and P is going to be the fraction of correct responses. So go ahead and answer A and B. Pause the recording to do that and resume to check your answer. Okay, so filling out the model, we see that as the trials increase, the memory, the amount of success increases. Although it does kind of slow down there, you'll notice it increases pretty fast at first. And then as you get to 7, 8, 9, and 10, the increase is slowed considerably. P approaches 1 as n increases, so it's getting closer and closer to 1, which again, remember, P is a fraction of how many you do correctly. So 1 would be perfection. You got them all correct. Part B, it says the percentage of correct responses is limited by the horizontal asymptote. Okay, and the horizontal asymptote in this case is 1 or 100%. In other words, you can't get better than 100%.